Okay, so let's make a start. We're having a look at chemistry paper 1. Hopefully we're going to go through the majority of the topics today. So in regards to what is on your chemistry paper 1, these are the paper 1 topics that will be assessed tomorrow. So we've got 5 topics. We've got atomic structure, we've got bonding, we've got quantitative chemical changes and energy. For anyone watching this on YouTube later out of this session, if you do want any, expert guidance, feel free to, contact me on that email address there. Okay, let's make a start then. So let's focus in on topic 1. Now, topic 1 is the basics. We're not going to spend too long on this. This should be pretty straightforward. We know that in an atom, we've got the electrons on the shells, we've got the proton and the neutrons in the nucleus. So I think we should be fairly straightforward. We should be fairly confident on atoms. We need to have a look at what isotopes are. So Aish, what are isotopes? Good. So isotopes are atoms of the same element with the same number of protons and electrons. So these are the same and the different numbers of neutrons. So isotopes have different numbers of neutrons. So that's what isotopes are. So be aware of that definition. Elements, well, they're found in the periodic table, and compounds, I think we can tick that off as well. Okay, so that was fairly basic stuff, the atoms and stuff. But what you do need to know is how the atomic model was developed. So let's have a bit of a look on how we know the atom is today. So the atomic model has kind of 4 main phases. So 1, 2, 3, 4. Now, in the first kind of discovery, or the first proposal was that all atoms are essentially small spheres. They're small circles. Yeah. So all atoms are small circles. The smallest possible sphere. Yeah, that's what the first proposal was. The second stage in the discovery was the plum pudding model, which said that small sphere, that spherical structure, has a Ball of positive charge inside of it. Then we moved on to, Rutherford, with most of the atom being empty space, and then finally we had the shells. So this is like generally what the atomic model looks like. So number one, we've got Dalton. Number 2, we've got J.J. Thomson. Number 3, we have got Rutherford. And number 4, does anyone know who came up with electron shells? Bohr. Yes, so number 4, we've got Niels Bohr. Okay, so what did Dalton say? Dalton said that all atoms are, first of all, the atom is the smallest possible thing to exist. And he said that atoms are spheres, they're little circles. J.J. Thomson said that basically the plum pudding model, which is a ball of positive charge with your negative electrons embedded in it. Rutherford came along and he did the gold foil experiment, and he came up with 2 things. He said that most of the atom is, what is most of the atom, Anaya? Empty space. And he said that we've got a small positive nucleus. We've got a small positive nucleus. And then Bohr came up with electron shells. So be aware of the atomic model and the development of this, just because, you might be asked potentially a 6-mark question on it. Okay, so we've had a look at that. Let's now move on to talking about separating techniques. So we want to know how we separate stuff. So let's talk about how we separate. First of all, let's just list the 4 different types of separating techniques. Can you name one, Anaya? Filtration, yes. Another type of separating technique is crystallization. What's another type, David? Distillation. And the final type of separating technique, does anyone know? Yes, so that's basically the same. It's chromatography. Chromatography. So these are the 4 types of separating techniques. Now we need to know what do we separate from this. It's pretty straightforward. So distillation, Anaya, what does distillation separate? What is it separating by?
Boiling point.
Boiling point, yes. So it's the separation by boiling point. Chromatography is the separation of inks and pigments. And then we'll talk about filtration and crystallization. Filtration is insoluble solid from a liquid. And Aish, what is crystallization? Soluble solid from a liquid, yeah? Soluble solid from that liquid. Now I'll just explain this. So crystallization, yeah? Let's say you got a glass of water, right? You got a glass of water, and in that water you're gonna have salt. You're gonna mix the salt. Is the salt visible now? It's not, right? How are you gonna get the salt back? Well, you're gonna evaporate. First of all, you're gonna heat the bottom, right? You're gonna heat. When you heat it, all the water evaporates. If all the water evaporates, what's left over? The crystals. Yeah, the salt. So does that make sense to everyone? So the way we do crystallization is we heat it using a Bunsen burner. We use a tripod and gauze. We evaporate all the water and we leave the salt crystals. Now this is really important. When you've evaporated all the water, yeah, you need to, number 1, leave the crystals. Yeah, you need to leave them. And then you need to dry the crystals. So this is what the mark scheme says. When you've evaporated all the water, when all the water's gone, leave the crystals, dry the crystals, and that's how you get crystallization. Filtration is pretty straightforward. Let's say I, put some rocks in some water. Filtration will get rid of the rocks. It's pretty straightforward. Let's talk a bit about distillation. Now, you need to know how we draw the distillation apparatus. So basically, what does the whole thing look like? Let's just do this quickly, just because you might get asked to draw it tomorrow. So it looks something like this. So it's roughly, something like that with your thermometer here. So look, we put the liquid in here, and below it we got heat. Yeah, we got a heat at the bottom, and here we've got some, we've got like a beaker which is collecting all of your drops of liquid. Now this is roughly the distillation kind of mechanism. So here we've got a round bottom flask. David, can you tell me why it's round bottom? Yes, all the water can be evenly heated. Yeah, that's the purpose of the round bottom flask. Aish, what is this thing called here? The condenser. Now, for condensing to happen, we need it to be cold. So that's why we have cold water, which goes in here. Cold water in. And we have cold water going out the top. Here we've got your thermometer. Why do we have the thermometer? Well, it's to look at the different the boiling point, sorry. Okay, so that was distillation. Chromatography, let's just do chromatography very quickly. So chromatography, so the way we do it is we get your chromatography paper, we put it in a beaker, etc. So we need to draw the pencil line, yeah? So we draw the pencil line, and then, so this is your pencil line. Why is the line in pencil, Anaya? Very good. And then look, we spot the inks. Let's just call it A, B, and C. And then we fill up the liquid, the solvent, at the bottom. So at the bottom here, we put your solvent in. Solvent's the liquid. Now what happens? Well, the solvent goes up, and as it goes up, it carries the inks, the pigments with it. As the pigments are going up, they form spots. For example, they might spot like this, etc. Now, where the solvent gets up to, let's say the solvent gets up to here, that's called the solvent front. Solvent front. Now, what can anyone notice about C? Why has C not moved? Does anyone know? So the reason why C has not moved is because it's not soluble in the solvent. Yeah, it doesn't dissolve in the solvent. So this is a very common question. C hasn't, budged. C hasn't moved. What can you make it to move? How do you make it move? Well, if you want to, separate C, you need to use a different solvent. Does that make sense? Yeah, you need to use a different solvent. We need to know about the stationary phase, the mobile phase. So, Aish, what is the stationary phase here? So what was that stationary phase? Stationary is still. So what is still here? No, quite. Stationary phase is the paper, the chromatography paper. Yeah, that's not moving. And the mobile phase is what's moving. For example, the solvent, the inks. Do you get what I mean? The other thing that we need to know about this is how we calculate RF value. So let's have a look at that. RF value. How do we calculate RF value, David? Solute over solvent, or ink over solvent. So if we have a look at this here, you're going to get your ruler in the exam, and let's say you've measured the solvent front, yeah, this here, you've measured it to be 10 centimeters. And let's say the question says, find the RF value for this, yeah? So you're gonna get your ruler again, you're gonna measure this, and let's say that's 5 centimeters. How do we calculate the RF value? Well, it's going to be, look, ink over solvent. So it's going to be 5 divided by 10, which is 0.5. And that's what the RF value is. Does that make sense to everyone? Okay. Right. We've talked about chromatography, distillation, and everything. And that's pretty much it for separating techniques. You should all be confident on it now. Okay, let's go back. I think we can tick off chromatography, distillation, and all the separating techniques. Right, we've had a look at the history of the atom. We've also had a look at electron structure. It's pretty straightforward, but we've got 2 electrons in the first shell, and then 8, 8, 8, 8, etc. We need to have a look at the development of the periodic table. Now, we've got a guy called Mendeleev. Now, can anyone... Oh, Hassan, are you in the meeting? Okay, I don't think so. Anaya, what did Mendeleev do? Oh, Hassan, you are? Okay, sorry. I can't see who's in the meeting here. Hassan, what did Mendeleev do?
Did he make the first periodic table?
Yes, he did. And he did one important thing. Yes, he did. And he also left gaps. That's the... Yes, very good. So he left gaps, and the reason why he left gaps is so the future elements, like you said, can be discovered. Sorry for that. I don't know who's in the meeting here. Okay, so that's pretty much it for Mendeleev. Just know that he left gaps for undiscovered elements. Right. The modern periodic table. What is the modern periodic table organized into, Aish? Yes. Obviously, or atomic number. Before it was the mass, right? So, that change. Right, metals and non-metals. Where are metals found in the periodic table? They're all on the left. And then non-metals are all on the right. Now, if you want to know the dividing line, you know where boron is? You've got a little staircase next to it. So the staircase goes something like this. Are you all familiar with this? So all of these are metals, and all of these are non-metals. Do you know what I'm talking about? Yes? Okay, let's move on. We need to have a look at group 1, group 7, and we need to have a look at group 0. So let's have a look at these. So group 1 is in, group 1. So it's got one outer electron. So let's just take, lithium, for example. Lithium is in group 1, which has one outer electron. What does it do? Well, it loses that outer electron. If it loses the outer electron, what charge does it become, David? +1. Now, what happens in group 1? As we go down the group, group 1, yeah, we get an increase in shells. So the shells increase as we go down the group. Now, that's the first point. So the shells increase. Now, if the shells increase down group 1, what can you tell me about the outer electron? Aish, what can you tell me about the outer electron? Yes, the outer electron is further away, right? The outer electron is further away from where? From the nucleus. It's further away from the nucleus. Now, we all know that the nucleus is positive. The nucleus is positive and electrons are negative. Now, this is called your nuclear attraction, yeah? Now, if it's further away, then we have a decreased nuclear attraction. So, because the outer electron is further away from the nucleus, there is decreased nuclear attraction. Decreased nuclear attraction. If there's decreased nuclear attraction, what can you tell me happens about losing it? Is it easier or harder to lose? Easier, yeah, it's easier to lose. So that's what happened in group 1. So just to emphasize to you, this is group 1. So reactivity increases down group 1 because there's more shells. There's decreased nuclear attraction, which means the outer electron is easier to lose. Does that make sense to everyone? Okay, let's now talk about group 7 then. Now, group 7 is the opposite. Group 7. If it's in group 7, Hassan, how many outer electrons does it have? How many outer electrons does it have if it's in group 7? 7, yes. So 7 outer electrons. So how can it gain a full shell? It needs to gain 1. If it gains 1, it becomes -1. So the same thing. As we go down the group, the shells increase. As we go down the group, the shells are increasing. So that's the same first point. As you go down the group, shells increase. Number 2, we need to gain an electron. Now, if we have a random electron floating out here, yeah? Let's say this is a random electron floating here, and the nucleus is positive. Which can pull it in more easily? This one, which is close, or this one, which is really, really far? What do you think, Anaya? The closer one, yeah? So this one can pull it in easily. So as we go down the group, there's an increased number of shells. Therefore, there's a decreased nuclear attraction. Same 2 points. Decreased nuclear attraction. If there's decreased nuclear attraction, then we can say that the reactivity does what, David? Decreases. And that's what happens in group 7. Yeah, so look, it's the same first 2 points. Shells increase, decrease nuclear attraction. Just remember that group 1 increases reactivity, group 7 decreases reactivity, and you'll be fine. Group 0, they've got a full outer shell. They're known as being inert. What does inert mean, anyone? Unreactive. Right. So it's fair to say we can tick everything off topic 1. It's the basics. Is everyone confident on topic 1? Okay, let's move on to talking about topic 2 then. Now we've had a look at this before, but let's recap it. An ion. Aish, what is an ion? Yes. How does it become positively charged? Yes. So look, an ion is an atom which loses or gains an electron. So an ion is an atom which loses or gains an electron. That's what an ion is. That's what, the definition of an ion is. Okay, let's have a look at the different types of bonding: ionic, covalent, metallic. We've had a look at this before, but let's recap it again. Ionic, covalent, metallic. Okay, so if you want to copy out a table like this, it summarizes it quite well. Right. Okay, ionic. Ionic is between a metal and a non-metal. Metal and a non-metal. And now, what's covalent between? Very good. And Hassan, what's metallic between? Metals only. Sorry, I don't know where my line's gone. Draw that again. Okay, ionic is the transfer of electrons. Covalent, what's covalent, David? Yes, but can you define it? Shared pair of electrons. Shared pair of electrons. Make sure you say shared pair. And finally, Aish, what's metallic? Yes. I'd say don't say C of delocalized electrons, because I've seen in mark schemes they ignore that word. Instead, you need to say that this is the electrostatic attraction. Electrostatic attraction between what? A metal ion and the delocalized electron. Okay, you need to say this. It's the electrostatic attraction between the metal ion and the delocalized electron to get the mark. Okay, now we can do the dot and cross diagrams. Let's just do that really quickly. So let's say NaCl. NaCl is ionic because sodium is a metal, chlorine is a non-metal. Now, sodium is in group 1, so it's going to have 1 outer electron, and chlorine is in group 7, so it's going to have 7 outer electrons. And now, how are they both going to gain a full outer shell?
Na is going to lose it. So it's going to gain.
Yes, so Na loses it and it goes there, like this. So Na loses it. Now, once we've done this, what do we need to do, anyone? Square brackets. And then we need to put the charge. So if NA's lost it, what charge is it? +1, and Cl is going to be -1. That's pretty straightforward. Let's just do covalent bonding quickly. So let's say we want to do fluorine, yeah, F2. Now fluorine's in group 7. So for them to, pair it, it's going to be a shared pair of electrons there. And then it's going to be, so 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that's fluorine, yeah? Shared pair of electrons. Finally, let's have a look at metallic. Now, the way you do metallic is, you need to draw it something like this. So look, if we have our metals like this, so this is metallic bonding. So pay attention to how I've drawn it, yeah? All of the atoms need to be touching each other, and they must be regular, yeah, like a line. So you need to fill these in with the charge, and then we need to put your delocalized electrons in like this. So you can label it. This is your delocalized electrons, delocalized electron, and this is your metal ion. So that's how you do metallic bonding. Okay, the other thing that we need to know about this topic is the melting point. So the melting point of ionic compounds. What is the melting point of ionic compounds? Anyone? High or low? High. Why do ionic compounds have a high melting point, Ash? Good. Which need a lot of? Yes. So high melting point because of the strong electrostatic attraction, which needs a lot of energy to overcome, which needs a lot of energy to break. Okay, let's have a look at the melting point of covalent. Now, covalent we can split into two. We can split into simple covalent and giant covalent. So let's do that. Simple covalent and giant covalent. What is the melting point of simple covalent? David. What's the melting point of simple covalent? Low. Why is it low? Yes, weak intermolecular forces. Good. Weak intermolecular forces. So why do simple covalent stuff like hydrogen, oxygen have low melting points? It's because of weak intermolecular forces. Giant, they have high melting points. Can anyone tell me why it's such a high melting point? Anyone? It's because of your strong covalent bonds. Yeah, so make sure you know the difference. Simple covalent is weak intermolecular forces. Giant covalent, it's strong covalent bonds. Is that clear to everyone? Yeah? Okay. Let's now talk about electrical conductivity. So let's just talk this verbally, just so we can get through everything. Ionic stuff, ionic compounds. Do ionic compounds conduct when they're solid, David? So do ionic compounds conduct when they're solid? No, they don't conduct when they're solid. Can anyone explain? So if you want to make a note, ionic compounds, they don't conduct when solid. So they do not conduct when solid. The reason why they can't conduct when solid is because the ions are fixed. If the ions are fixed, they can't move, they can't carry the electrical charge. However, they can conduct electricity when they are in a liquid or they're molten. And now, why can they conduct when they're liquid or when they're molten, melted? Yes, very good, because the ions can move. The ions can move, they can carry the charge. So make sure you make a note of this. Ionic compounds don't conduct electricity when they're solid because the ions are fixed, they cannot move. They can only conduct when liquid or when molten. Molten means melted. Okay, let's have a look at metallic compounds. So, Hassan, can metallic compounds conduct electricity? Can metals conduct electricity? So metals actually can conduct electricity. So, Aish, can you explain why metals conduct electricity? Which type of electrons? You need to be specific. Yes. So the reason why metals conduct electricity is because the delocalized electrons can move and they can carry the electricity. By the way, can I request, for people to mute just because there's, shuffling noises and stuff? Obviously, when I ask you a question, you can unmute. Right. Let's have a look at covalent. Now, we need to know about giant covalent structures. Now, there's 3 types of giant covalent. We looked at it yesterday, but let's do it again. We've got diamond. We've got graphite. What's the final one, Anaya? Graphene. Okay, now, they all have a high melting point. Why do they have a high melting point? It's because they've got strong covalent bonds. Now, we need to talk about the electrical conductivity. So, diamond does not conduct electricity. Diamond cannot conduct. David, why can it not conduct electricity? Good, because diamond forms how many bonds? 4 bonds. Diamond forms 4 bonds. Nothing can, move to carry the charge. Graphite and graphene, they can conduct electricity. Why can they conduct electricity? Because they form 3 bonds. 3 bonds. Now, let me just explain this in a bit of detail. Now, you know from alkanes, alkenes, that each carbon atom forms 4 bonds. Now, if graphite and graphene are forming 3 bonds, then can you see we've got delocalized electrons here? Yeah? So the reason why they conduct electricity is because they can carry them. These delocalized electrons can carry the electricity. So to summarize, diamond does not, graphite, graphene does, because they've got these free electrons. Okay, so I think we can tick most of these off. So okay, let's just do quickly states of matter. It's really simple. Solid, liquid, and gas. Hassan, what do we call when we go from a solid to a liquid? Yes, so solid to liquid is specifically, melting. And then liquid back to solid is freezing. What else is there? How do we go from, yes, condensation, so that's gas into liquid, and then liquid to gas is evaporation. And then we've also got sublimation as well. So that, that's pretty basic year 7 knowledge. Okay, let's move on. Let's talk a bit about quantitative chemistry. Now, this is maths. Now, you're bound to get a maths equation tomorrow. You need to know these 2 equations. You need to know mass, moles, MR, and you need to know moles, concentration, and volume. Remember these equations. The other thing that you need to know about this is unit conversions. So David, how do we go from centimeter cubed to decimeter cubed? It's the opposite. Divide by 1,000. Divide by 1,000. It's fine. You can make a note of it and you can remember it for tomorrow. Centimeter cubed to decimeter cubed is divide by 1,000. Make sure that you make a note of this. Okay. The best way to do quantitative maths is by doing questions. So let's have a look at this. Okay, so this is an example question. So let's go through this. So we've got sulfuric acid and sodium hydroxide. So look, how do we answer this question? Well, first of all, you need to figure out which equation you're using. If we want to work, if there's loads of, decimeters concentration volume, we're going to use the moles concentration volume one. So once you've figured out the equation you use, you then make your table. This is how you make your table. Moles, concentration, and volume. So if you lay it out in a table, it makes it much, much more simpler to do. Okay, now we fill it out. So H2SO4 has a concentration of 0.4. So look, we write 0.4 here. It neutralizes. Just a second. Okay, so the NaOH concentration is 0.2. And what's the volume of NaOH, Aish? The 0.1. Now look, once you filled out the table, it's pretty straightforward. You just go about filling the boxes. So look, we want to calculate moles here. So if we have a look at our equation, you multiply them, 0.2 times 0.1. So that's going to be 0.02. Yeah? 0.2 times 0.1, 0.02. We got the moles. Now, we wanna find out how much acid was used. We want to find out this. Yeah, that's what we want to find out. So look, we can calculate volume by moles divided by concentration, but we don't have moles yet. So the way you find moles is you use the ratios. If this is 2 and this is 1, how do we go from 2 to 1? We divide by 2. So the same thing here, we're going to divide by 2. And we're going to get 0.01. So look, to find the moles, we use the ratio. Yeah? The ratio doesn't work with this or this. It doesn't work with these two. The ratio only works with moles. So only this. So now we find the volume. It should be pretty straightforward. What are we doing? We're doing 0.01 divided by 0.4. And the answer should be 0.025 decimeter cubed. And that's how we do these types of questions. Does that make sense to everyone? Okay, let's move on to doing this one. Now, we don't have an equation here, so we need to make the equation. So potassium oxide plus water goes to potassium hydroxide. So potassium oxide, KO. Now, potassium is in group 1, so what's the charge, David? +1. And Aish, oxygen's in group 6, so what's the charge? So how do we find the overall formula? We use the swap and drop method. So what is the overall formula, anyone? K2O. K2O plus H2O goes to potassium hydroxide. What is potassium hydroxide? Anil? So what does hydroxide mean? Yes, so OH. Yes, OH. Now look, once you've written out your equation, we need to balance it. So if we've got 2 Ks there, we need 2 here. And then I think it's balanced. Yeah. So look, once you've written out the equation, once you've balanced it, now you do your table. We do mass, moles, MR. We do your table like this. We fill it out. So we've got 9 grams of water. We've got 56 grams of this. We want to find out this. So, you do it quickly, and then you'd use the molar ratio. So look, 2 to 1 divided by 2. So divide it by 2, and then you'd go from there. Does anyone have any questions on this concept? I'm not going to complete it because I want to do different the other topics, but that's how you do it. Are you good with this, David?
Yeah.
Yes. Okay. So that's basically it for quantitative chemistry. It's just these 2 equations and that unit conversion. But look, if you do the table, it will make it really simple for you. Let's move on to talking about chemical changes. An acid. So an acid releases H+ ions. We need to know the difference between a strong and a weak acid. A strong acid fully splits into H+. So a strong acid, for example, HCl, goes into H+ and Cl-. Whereas a weak acid, what does a weak acid do, Anaya? Partially splits. And the way we represent the partial splitting is by a reversible arrow like this. Okay, let's have a look at an alkali. So an alkali releases OH- ions. So a strong alkali, for example, this fully splits into Na+ and OH-. This is what makes an alkali. And a weak alkali partially splits with your reversible arrow. We need to know about the pH scale, but that's pretty straightforward. Okay, so now acids react with a bunch of things. So we need to know some reactions here. So we need to know acid plus metal. We need to know acid and metal oxide. We need to know acid and alkali. And we need to know acid and metal carbonate. So let's just go through these verbally, just because it should be basic knowledge before, day before the exam. Acid and metal goes to what, Aish? Salt and hydrogen. Hassan, do you know how we test for hydrogen? Yes, exactly that. So the way we test for hydrogen is we get a lighted splint and that makes a squeaky pop. Very good. Anaya, do the second equation. Acid and metal oxide goes to? So we always go to a salt. We always go to a salt, and if it's got oxide, it goes to water. Yeah, salt and water. Acid and alkali is also salt and water. And David, what's the final one? No, it's carbon dioxide. So salt, water, carbon dioxide, 3 things. So look, acid and metal carbonate is salt, water, carbon dioxide, 3 things. Okay, good. Let's move quickly on to, so look, I'm skipping past these bits because I want to get on to electrolysis. Let's talk about electrolysis. Now, I've taught electrolysis to most of you in detail. Let's just do it again. So this is how we do electrolysis. So this is your electrolysis apparatus. So let's say we've got NaCl in our here. So this is NaCl. Okay, so and here are your electrodes. Now let's say the electricity is flowing this way. Yeah, the electricity is flowing this way. All the electrons are going to this electrode. So Aish, what is the charge of this electrode? If all the electrons are flowing to it? Negative. And the other one is positive. Okay, let's have a look at our NaCl. So look, when we turn on the electricity, the NaCl splits. The NaCl splits into Na plus and Cl minus. Now look, opposites attract. So Anaya, where does the Na plus go? Good, to the -1, and the Cl minus goes to the +1. So look, all your Cl minuses are here and all your Na pluses are here. Does anyone know the observation we get at the positive electrode? So if you've got a lot of chlorine, chlorine is a gas, so we get bubbles. We get chlorine gas bubbles. And the observation we get at the negative electrode is we get the sodium metal, which is kind of stuck to the bottom. Okay, now look, we've got the positive and negative electron, a special name. You need to remember panic. Positive anode, negative is cathode. So this is cathode, and this is anode. Positive anode, negative is cathode. Okay, the other thing that you need to know about this is how we write half equations. So we need to know about oil rig. So David, what does oil rig mean? Loss of what though? Electrons, yeah? Oxidation is loss of electrons, reduction is gain of electrons. So if we have a look at this, yeah? If all the electrons are flowing this way, and they're flowing into Na+, which is gaining electrons? Right, which is gaining electrons? Na+, because all the electrons are flowing to it. So look, the Na+ is gaining, and the Cl- is losing. So Na+ is reduction, and Cl- is oxidation. Does that make sense to everyone? Okay, we need to know how we write the equations then. So let's have a look at the reduction equation. So let's have a look at the equation for reduction. So Na+ plus E- goes to Na. This is reduction. This is reduction. Now I'm missing something from this and this state symbols. So solid, aqueous. Now oxidation, let's just do the oxidation one. Now oxidation was loss of electrons, but we can't put a minus there, so this is how we do it. So Cl- aqueous. Can anyone walk me through how we write oxidation equations? Yes, we put an arrow, and then it goes to what? Is Cl a solid? It's a gas. Now chlorine is in group 7. And what do you know about group 7? Everything is Cl2, everything's, yeah, diatomic. So look, it's going to be Cl- aqueous going to Cl2 gas plus E-. Now, what's wrong with this equation? Can anyone shout out? It's not balanced, so we put a 2 there. And if this is 2 minus, and this is 1 minus, we need to put a 2 there as well. So they're both 2 minuses. That's 2 minus, this is 2 minus. So look, this is your oxidation equation. Okay, make sure you know the difference. This is your oxidation equation. And that's it for electrolysis. So it's fair to say that we can tick these off confidently. Let's now move quickly to doing topic 5. Now, this is all about your exothermic, endothermic reactions. We've done it before, but let's recap it before the exam. Exothermic releases energy and endothermic takes in energy. We need to know the different, the type of graph. So on the y-axis, what do we have on the y-axis, David? Oh, so progression's on this. So progression is here. So this is progression of reaction, and here we have energy. Okay, let's go through this quickly. Let's have a look at an exothermic reaction. Exothermic looks like this. Whoops, sorry, that's endothermic. Endothermic looks like this. We have your reactants, we have your products, and we have your activation energy here. So we have activation energy going all the way to the top. This is activation energy. And now, what is activation energy? For the reaction to happen. Okay, Hassan, what does a catalyst do? Yes, it increases the rate of reaction without being used up. A catalyst lowers the activation energy like this. And here we can label this catalyst. We can do the same for exothermic. Exothermic one is, let's just do it quickly, it's just so everyone is absolutely sure. So exothermic looks like this. So this is your exothermic one. So here we still have reactants and we have products, but in exothermic, the products are lower. Again, we've got your, we've got your activation energy, and then we can draw your catalyst in like this, and that would be your catalyst. Okay, so that's a quick recap on exothermic and endothermic reactions. Right, we need to know about bond energies. Now, bond energies is a really simple concept. You have it drawn in the exam most of the time, so I'll just draw it for you. Okay, let's have a look at how we calculate the bond energies then. Whoops. It's pretty straightforward. We're going to look at the table and we're going to add everything up. So a CH bond, what's a CH bond, David? If you look in the table, 435. So we add 435, 435, 435, 435. Hassan, what's an OO bond? So if you look in the table, 497. So 497, 497. Yes. So look, we're going to add everything on the left. You're going to do the same. You're going to add everything on the right. So add everything on the left-hand side, add everything on the right-hand side. And how would you get the final answer, Aish? Yeah, exactly. Like you take them away. So you take the left minus the right. So once you've calculated a number, I don't know, let's just say 2,000 and I don't know, 500. You're gonna do 2,000 minus 500. The left-hand side, the reactants minus the products. The left-hand side minus the right-hand side, and you're going to get your answer. What happens if we get a negative number? Let's say the answer is minus 598. What does this mean, anyone? Oh, the reaction's exothermic. Yeah, if it's negative, the reaction's exothermic. Yeah, so make sure you make a note of that. If you get a negative, that means that the overall reaction is exothermic. So look, bond energies is easy. Calculate a total number for the left, and then the right, and then you're going to do the left minus the right. If your answer is negative, that means it's exothermic. If it's a positive, it's what, David? Endothermic. Okay, right, let's go back to this. I can say with confidence that we can tick all of them off really nicely there. And you'll be happy to know that we've covered all of chemistry paper 1 now. So we've done all of the, 5 topics. So, make sure that you go away and you revise now. But does anyone have any questions on anything that I've done today? Hello?